morning, welcome to my laboratory. This is going to be a revisit of the Ainslie Quantum-17 work, and I have a lot to show here, so I'm going to go pretty quickly. This circuit right here is the exact 555 timer circuit using the exact component values that Ainslie published in the 2002 Quantum magazine schematic. $50K 10-turn pots, NE555N, and the same diodes, resistor values, and capacitor values that are listed in the Quantum magazine article. Okay, and what I want to do is show, first of all, the duty cycle and frequency range of this unit. Okay, and this is what it looks like. Here's the baseline of that channel, and there's what it looks like when it's on. So you see we have a long high time, very short off time, long high time, very short low time. Instead of the 3.7% on, we have a 96% on, the exact inverse of what is claimed in the Quantum article. Okay, and I'll show you here by putting this screwdriver onto the duty cycle adjustment pot. You can see that I can go shorter and shorter and shorter off times, and I can go longer and longer and longer off times until I reach the end of the adjustment, which is right about there. That is the shortest on time and the longest off time that the original Ainslie article circuit will produce. Okay, now let's see the frequency. I'll move over to the frequency pot now, and I'll adjust the frequency. So you can see as the frequency changes, the off time doesn't really change, right? So the duty cycle does change. So at a very, very, very low frequency, then you do start getting even shorter off-time duty cycles. But there is no way with this circuit that you can actually produce the 3.7% on at 24 kilohertz that Ainslie claims. Okay, unless you use the magic of DPDT. I'll show you how this double pole double throw switch is wired. Right now I'll show you the effect of it. Okay, instantly we have the correct short on time, long off time duty cycles. Right? And now let's go to the frequency counter, and with the frequency adjust potentiometer, let's get our frequency back to 2.4 kilohertz. Okay, there's our approximately 2.4 kilohertz. And that's what it looks like on the scope trace. Now let's narrow out that duty cycle. I've been doing all this with the main battery to the power section disconnected, by the way. So now let's narrow that duty cycle on down. Until we get a nice thin on time. Okay, I want to actually still be able to see some thickness to that. But that's under 10%. That's probably 5% on right there or so, something like that. Okay. And let's see, that's changed our frequency reading a little bit, so let's fine-tune the frequency. Get that back down to 2.4 kilohertz. Okay, so now we're right about 2.4 kilohertz with the frequency, and we have nice narrow spikes, so we're not going to adjust those guys anymore. There's the gate control pot there. Alright, so now what I'm going to do is just unhook the frequency probe. Like that. Oops. Try this with one hand. Ouch. Okay. Okay, so I got the frequency probe disconnected now. And now I'm going to go ahead and hook up the battery. Okay. So we have about 60 milliamps now of current showing on the DC meter. And let's go ahead and put this stuff back where it belongs. Put that down there. Go to 5 volts per, or 10 volts per division. This is the gate signal, remember. Now here's the MOSFET drain signal at 50 volts per division. Okay, and I guess you can see that there's a pretty good little the baseline now on that channel is right there. So we're seeing the 24 volt battery voltage, and then we're seeing off, on, off, and a spike, just like we should be seeing. And notice that that spike goes up to 50, 60 volts or so, right? And we're not getting any heating, and we have about 60 milliamps of current. And here's what happens when I vary the gate, the gate pot a little bit. If I go, I've got the gate pot turned all the way to maximum resistance now. So if I turn towards minimum resistance, watch what happens to the signal. Turning, turning, turning. See how that spike is starting to increase now? And then right about there, the thing shifts modes suddenly and goes into a higher frequency, and now I'm just turning it back and forth around that point there. Okay, so I believe that this is what Ainslie is referring to when she says it goes into oscillation. And that point right there, and the signal gets very narrow. This is before the oscillation, 100 volt spike there. Now turn it a little bit more. There's the oscillation mode. The spike gets very, very narrow, and then you can't really see it, but the positive extent of that spike now goes up 50, 100, 150, 200. It goes off the screen, so that's over 200 volts in that spike now. Okay. And of course, if you look at this at a slow enough time base, you see lots of noise. Alright, so there's, it's not producing heating, it's not producing current, but it is producing that nice spike that you can just barely see on my oscilloscope screen here, okay? Now I want to show something else. I have here a 100 microfarad 200 volt capacitor with a 1N4002 diode hooked to it, and these are the leads that go up to that voltmeter up there, okay? And so we're looking at the voltage on this capacitor, and I have the blue wire over here going to the MOSFET source and the red wire going to the MOSFET drain. Okay, so this is where the recirculation diode goes in some of Ainslie's schematics. So now I'm going to hook up, make the connection like that, and now let's look at the voltage on that capacitor. Remember, we're just giving this a 24 volt supply. Alright, so this is the spike voltage that's being siphoned off onto that capacitor by the diode. Okay, and let's see, which mode are we in? Yeah, this is the, let me put it into the non-oscillatory mode, which is this mode here. And it looks to me like the spike goes up to just under 100 volts there. So we're seeing the voltmeter climb. So there's plenty of amplitude, voltage amplitude in the spike, and that is coming off and being siphoned through and putting the charge onto that capacitor. Okay. Now, without the capacitor there, what happens to the spike? Does it recirculate through the system and charge the run batteries over here? Or is it dissipated as power heating in the MOSFET and maybe in the load? Let's see, rate of charge is starting to go down a little bit. This is almost 62 volts. So now what I'm going to do is use the gate pot to shift into that higher oscillation mode right there, and that has the steeper spike. So I guess you can see we're still climbing up in voltage on that capacitor. We have a 24 volt battery stack, and we're well over twice the battery voltage, and we would get to 3 times the battery voltage on this capacitor if we were willing to wait long enough. Alright, now what happens if we switch this thing into the Quantum-17 mode with a very long on-duty cycle and a short off-duty cycle? Let's see, here we go. So now we have the spike again, but that spike is even higher and even more radical, and you can see that the charge rate has now gone up. Right? So this is in the Quantum-17 mode now. This is what you get when you use the Ainslie circuit directly. You get a high current draw. You get got a glare on there. Sorry about the light. You get definite load heating. You get a high current draw, and you get a spike amplitude that is recirculating well over 3 times the battery voltage. This should go up to 200 volts. If I wait long enough, that capacitor voltage will increase all the way up to 200 volts. And to show you that that is real, what I'm going to do is unplug the battery. That stops the current. Hopefully that stops the heating. Look, I've unplugged the battery and the load is still warming up at 0 current. Free energy? I don't think so. Okay, so that voltage now is slowly leaking off the capacitor. And so what I'm going to do is just show you that it's real. This is 100 microfarads. I don't know if that actually showed up or not, but that was 70 volts at 100 microfarads there. All right, thank you very much for watching.